Okay, now there's a couple of extra topics, and one of the extra topics here after the frequency domain is the rotational dynamics, and how we're going to use that to deal with the theory of capital. So in the classical kind of Newtonian theory, as you'll get into in dynamics in your first year, they really have two ways of doing dynamics. One is this translations, where you have momentum and forces going in translatory motion. The other is rotational motion, okay? They have an F is M times A, and that becomes tau is I times omega dot or something, right? So there'll be an angular velocity instead of regular velocity. There's a torque instead of a force. And there's a moment of inertia instead of a mass, but otherwise the theory is exactly the same. And this is kind of you would think like, hey, how is this possible? And there's a couple of reasons why this is possible. Okay, so after Newton did his thing, I think it was Euler who figured out, and Lagrange a little bit later, that you could do the same stuff for rotations. It's a little bit different in 3 dimensions, gets a little bit more complicated, but not really. So we have in basic mechanics, we have two theories, right? So you have just the translational theory and the rotational theory, but they're really different, okay? And one thing that's different is that in the plane, there are 2 translations, but only 1 rotation, right? So it's weird. And in 3 space, how many translations are there? 3? How many rotations? 3. Yeah. So it jumps from 1 to 3, the rotations. You know? What would that be? I mean, it's clear that if you're on a line, how many rotations are there on a line? 0. Yeah, 0, right? How many translations on the line? Yeah. Okay. Then in a plane, you have 2 translations. All of a sudden, 1 rotation shows up. And then, so it goes from 0 to 1. And then from where you have add another translation, all of a sudden you have 2 extra rotations that show up. Why is that? I'm asking these questions because all of this is going to be relevant. Why is that? What do you think it is? Huh?
Like you can now rotate around the axis that were in the plane, which you couldn't before. When you're in the plane, you can only rotate on the one that's perpendicular.
Okay, the right answer is in there. It's a little bit going every which way. For a rotation, you need a plane. Okay? For a translation, you need a line. How many planes are there on a line? Yeah, 0. How many planes are on a plane? Yeah, 1. How many planes are there in 3D space? Well, 3. 1, 2, what's the third one? This one. Okay? So if you want to know translations, just count the number of lines in your space, you know, and if you want another rotation, just count the number of planes. So if you pick in 4D space, what are you going to have? You're going to have like, how many planes? So it's like 4 choose 2. So I don't know, I think it's 6 or something. You can figure it out, the number of planes. I think you have 4 dimensions, and you got to choose combinations of 2 of those to form a plane, right? So it's 4 times 3, which is 12, divided by 2 factorial, so it's 6, I think. Anyway, okay, so there are differences, okay? There are differences, and they can be quite confusing. Now, we're going to exploit those differences because there's a difference between trading commodities and a theory of capital, when you have some resource and the return is on the resource. There is also a big difference, and the difference is related to this business of translations versus rotations, okay? That's what's pretty about it. So this is real economic engineering. So up to now, we've just done only translations. That's what Newton did. Now we're going to add this, and we're going to generalize it a bit. So we only look at these rotations, but you can generalize. You can look at hyperbolic rotations and other things. Okay, so that's what we're going to do. Now, let's go now back to the theory of economic theory. So when you have commodity trades, you just have apples and oranges, you have all this stuff, and they all go along a line, and that line is exactly the account, okay? That you have. But in society, or in economics, I mean, there's more than that. We have a notion of capital, okay? The stuff you have, and associated with that capital is a return that you get. So if you have financial capital, you're going to make some financial return. So if you have some bonds, you're going to make some, you get some coupons, some interest payment, okay? If you have land, you're going to get crops. So there's some kind of relationship between the two. That's unlike apples and oranges. You know, apples and oranges are just like unrelated. I mean, they could be related, but they're not, okay? You know, physically, they're unrelated. They're just economically. You can have a price for this and a price for that. The price for land and the price for the crop, they're going to be related to, okay? So if you have stock on the stock exchange, then what's that worth? Okay, it's a piece of paper. It's only worth the earnings or the dividends you get on it. What's a bond worth? Well, it's worth the money you receive. That's the interest plus your principal payment back. Okay, so this relationship is the one we're going to capture. So we're going to now say that there are two types of. We're going to distinguish between one special dimension, that's what we're going to call the capital kind of dimension. All right, one special quantity, capital, that goes on a completely different time scale than the returns on these capital, okay? Right? So if you look at a business, you'll see that that's how they operate. So a business has this capital, whether it's machines or some financial capital, I don't know, and they make all that returns, okay? Now, who is doing the returns? That's usually an operations department. So they're running the day-to-day operations of the firm. They're booking all the returns in the P&L, right? In the income statement. That's where the returns go. So the cost of goods sold, and sales and income and expenses, and they all go in there. All right. But the company, before it could start doing operations, it has to have some capital to get going. So there's going to be an investor. Usually, it may be owner, and those are the owners of the company, and they put money in there. Okay. It's not the same. That money doesn't show up on the income statement. Okay, we don't call it income. We call it an investment. All right, and there are separate accounts for it. So we make a distinction between income that's coming in and an investment that's coming in. It's a very different flow. Right? So all of you were doing, multi-ports. You remember you have to have, and that's what. There's a separate port for investment. You can't throw it all together, right? Okay. And we all feel that these investments and this capital must be something different. The time scale is different, and it gets booked differently. So we're going to make this distinction. You can keep the capital fixed, and a lot of people do. So the company gets capitalized, and that's done one. That's called the initial capital. And then they start running, all those things. But nobody changes the initial capital, okay? No? So it's just, you can do a share emission. So for so many shares, the company puts them out. Okay, they get traded on the secondary exchange. Well, as the company's concerned, they're booked at par value, aagio in Dutch, okay? And they're there. And that's the initial capital of the firm. The rest are retained earnings. So you just look at your income statement, you get these earnings, and you can reinvest it in your company if you want, but you don't have to. Right? You can pay it out as a dividend. It's different money. So this initial capital is conserved, in a sense. Okay? So every time a company places its books, the initial capital will be conserved unless a capital contribution or distribution is made. All right? Now, in our operations, we don't talk about contributions and distributions of capital. No, we'll talk about income or expense. Well, I said here income and outgo, but there's a whole bunch of things depending on whether it's a product. So if it's just money, we say income, it's going in, and expense goes out. Inflow and outflow when they're goods in an account. Consume, produce, Store, destock when it's an inventory. I don't know. This list goes on. I just put some generic terms. Now, the way we're going to think of capital is as a radius, okay? That's the thing that stays relatively fixed. You can extend it, but it's a different type of behavior than this return, which we're going to think of as the angle, right? So this distinction between capital and return is the same distinction that now we made between the radius here, r, and some kind of angle theta over which this radius sweeps out, right? Okay. So the angle gets made on the radius, as it were, because you will look at this distance here, let's say dl, and then you look dl, r, and that will be the change. All right. So you see, it's like what you receive divided by that, so it's the returns over the capital. Right? Okay. It's like an angle. So that's the big picture here. Now, I think that everything is always a rotation, and that's the only thing you have. But in fact, this idea of a rotation has been built out by mathematicians in something that they call group theory, especially in Lie groups, and that means there are continuous groups of transformations. So transformations, rotation is a transformation. And if you can do it infinitesimally, they call them Lie groups. This guy Lie, who invented them. And they're called groups of transformations. And the idea in mechanics is that what you do is you look at your equations of motion and you look under what transformation group they are invariant. Okay? And that's how you describe these situations of what is capital and return. Now, if you have no capital, you will deal in with translations. Okay, that's the commodity theory. So the commodity theory, let's go back to the Newtonian case. The assumption is that the space around us is homogeneous. So I can do an experiment and pick up the experiment and place it somewhere else in the laboratory or in another guy's laboratory, and you get the same result. Okay? The laws of physics of mechanics are invariant under changes or in translations in space. Okay? Now, we modeled the demand laws after the laws of physics. That's the Newtonian Mechanics of Demand. And what that means is that for the commodity theory we've developed, the laws of economics are invariant under shifts in the amount of goods. Okay? All right? So the commodity theory, what we say is we recognize it because the whole theory is invariant under translations. Okay? Now, there are other invariance groups that are, that you can look at, and those are the ones that will you do when you do rotations. Okay, so in a rotation, it's not invariant on the shifts because there's a special point, which is the point around which you're rotating. And you can look at the rotation from here, and you'll get some rotation, but it will look really complicated, and the thing will move all around. So that thing is not invariant under translations. What is this invariant under? Rotations. So you can take it and it will rotate it. And then, if you have a space that's invariant under rotations, then, okay. Then you have a different symmetry group. Now you can have spaces that are invariant under shears, your rotation, different types of rotation that are called hyperbolic rotations or boosts. This is used in relativity theory, because time is a little different. You can't rotate into time, you have to hyperbolically rotate. But we'll get to that. Okay? But that's what Einstein discovered was the symmetry group of space-time, right? So shear is like a rotation on a very small or over a very large rate. All right. So let's now look at these, but that's the picture here. All right. Now Newtonian mechanics, what we do is we look at space and we say it has two invariances. It has one invariance under translations, so we can do Newton's law, and it also has an invariance under rotations when you compose it with the appropriate translation. So if I take some system and I take the whole thing and I go over there and I rotate around the new, position, then everything is okay, right? And we say that the space is homogeneous and isotropic, all right? And we allow these two operations. That's all we allow. And that's how we get these two theories, all right? Now we'll see that this type of thing, when we have two groups simultaneously, will give us a picture for operations and net income and things like that. To get to it, it's a bit of a long ride to get to these things, and for an extra topic as well, but it's very interesting. Okay, so that's as the background. So what I want to do is first just go back to the simple thing, translation. So here we have space. Here is one commodity, apples. Here are the pears, right? What we're saying is, if you have this stock amount and you're kind of demanding, now not the same as just moving yourself over here and start demanding here. This I just took this out of Wikipedia from there. All right. Now that's what the theory of demand says. Now why is that reasonable? It really is not so reasonable. If you think of real life, because so many apples, why would I demand more? Okay, and that is not what the theory of demand says. You see, the theory of demand, you can see this is the demand line, and they put a Q there, but it should be a flow, all right? And here's this price. What they look at is they say this price is only determined by how fast you go, right? How much you're demanding. There's nowhere in this whole graph do I find something that tells me how much stock I have. Okay? So in the theory of demand itself, the idea of scarcity doesn't come in. You're always flowing, you're just eating it. This is very typical of economic theories, only flows, right? So there's no stock to say, all right, I got too much, okay? Only I'm getting too much, or I'm getting, So this theory of demand is indeed invariant under these translations, okay? Right? So mathematically, this is how we view a translation. So you take this point and you add a delta Q here and delta Q here, this guy called T for translation. But that's not enough. What you want is that also all the laws, right, all functions, a bunch of functions are invariant under this, all right? So you need not, when you move this, you want to say that this function also doesn't change when I move it around. It's not dependent on, this demand function doesn't depend on how much you've already consumed. That's past, right? It's just on the current demand. So it's like a stock market. Who cares what's being bought in the past? You're going to look now at what's going on. Okay? And then when you figure this out, we'll see this is not totally trivial. You'll find out that if this is the case, there's a conserved quantity, okay? And that conserved quantity here is price. In mechanics, it's momentum. Well, momentum is a conserved quantity. Why? Because space is homogeneous. We can shift this thing over there, and then momentum comes out to be. That's the modern view of why you have conservation, right? Now, if you add a spring to this thing, and you make that part of your space, the spring, then this space is not homogeneous because you'll be stretching it and momentum will not be conserved. So you've got to understand that the springs are not part of the space, okay? The space is springless, all right? Even gravity, which we feel is not really part of the space. It comes from somewhere else in the Newtonian framework, all right? You've got to put it in there, right? You've got to put a planet there and go like, hey, I got gravity, but space. If I take out all the planets, then I have space, okay? All right? And in that space, In that vacuum, I can have no friction noise, and then I can start doing Newtonian mechanics, and I know F is M times A. That's the picture you got to take. And this economic commodity space is the same. See, if you can just move things around, and the law of demand will be valid. But if you then start adding stuff, okay, then you got to add it. So you got to add this capacitor or this store to say, well, I have enough. I get some dependence on where I am. That's how you have to view this, all right? So it makes sense to say, well, I haven't added anything. And in those conditions, price becomes a conserved property, okay? So if you take space and you don't add gravity and springs and all kinds of potential forces, then momentum is conserved, okay? Otherwise, momentum is poured into the system, gravity pours it in, and it starts accelerating. All right? Okay. Now I agree that Einstein changed that and made gravity part of the space. So you have to warp the space in order to get it in. All right. And then you're okay again, and then gravity becomes part of the structure of the space. But this is not productive to take this point of view here. It's way more productive to take the point of view that we just take in engineering, just having an extra force that just shows up. All right. Okay. Now, if I have a commodity space, say apples here and oranges here, these are oranges and these are apples, then of course I can shift this. But can I rotate this space? Can I just do this, right? And it's then the same. Yes.
What I don't really get is you can switch it, but it changes, right? So you can translate it.
Yeah, slide it like this.
Yeah. But it does change. So it's
What
not,
changes? What changes?
well,
What is
the
the
amount of commodities that you're having changes.
Yeah. So you can take this laptop with your experimental setup and the position would change.
Yeah.
But how does it change the results of your experiments? If you put it in a different place.
Yeah, that doesn't change.
But now you attach a spring to it and then you move it, then something's going to change
Yeah.
the force. So think away that spring. And you take your thing and move it over there. Right?
Yeah.
Okay?
So you're like changing your reference as well.
Yeah, your location, what you're doing.
Yeah.
Right. What's happening here? So the demand is so much oil. This is several barrels of oil at this price. How does it change the fact if I tell you, well, 100 years ago, somebody also did this, okay? And so much was accumulated in demand, Every day is a new day, right? Okay? So nowhere in this graph does it say how much has been demanded and integrated. Right? You just look at this moment and you say, then this determines the price. The price is not determined by how much has been bought and consumed beforehand. Okay? Get it?
Yeah.
If it does, then there's something you haven't modeled, right? You got to add that in the model. That's the right thing to do. So your assumption is this space is totally clean. The only thing that happens in your space is if you take an inertial mass and you try to change its velocity, it's going to cost you something. Right? That's cool. But it can't be you're thrown back in your seat because all this stuff is not, or somebody's pulling at you, then it's got to come from outside. It's not part of the space, okay? This is how it's set up. That's a good question because it's kind of a cleansing of the mind that has to be done here, okay? Where you say, all right, the space is like this white canvas on which I'm sitting, and I have some structure in it, right? But not everything, right? Some stuff I'm going to add, and it becomes a lumped element or this, right? So storage is something that's not part of the space, of the configuration space. You've got to put the element in there. All right? Okay? All right. That's what we call Galilean invariance or Euclidean space. It's basically is Euclidean space, right? So Euclidean space, you can shift it around. It doesn't have an origin. Euclidean space. Okay? And Euclidean space has one more thing, you see. See, that commodity space doesn't have in principle. And what is that? That is that it's also invariant on how you turn it. So it has a distance. So if this were a Euclidean space, you would calculate the distance of this vector. And you will do this by delta q1 squared plus delta q2 squared, and you take the square root, right? And Pythagoras taught you that, right? So that's Euclidean space. And because of that, you can rotate it. Because when you look this distance, if you rotate it, how is this distance going to change in one, right? But now suppose this is a commodity space, and these are apples, and these are oranges, right? Now you will have to take apple squared, okay. A little bit weird, but okay. And then I have to add it to oranges squared. You're told not to add apples to oranges, okay? You can't do it, right? So this space is then not invariant on the rotations. Obviously not, because this is this weird stuff you're doing, right? You know, if you make a new product like this, then, you know, there's no reason why your law of the band will just work out in these new things, all right? Okay? So somehow extra structure has to be added to the space to make sure that it has this metric, this way of measuring distance, you know? And commodity space doesn't yet have. It does have enough to draw lines, okay? All right, because you know, I go apples and oranges. So the products themselves, they define a sort of a netting, right? We call it a fibers also, all right? But they don't define the rigidity that you can rotate it, okay? That Euclidean space does have, okay? All right? Now, why does Euclidean space have that? And well, I don't say no. Well, it means, you know, okay, let's say first what it is. If mechanics happens in Euclidean space, it doesn't because it happens in a slightly more complicated space, but in the Newtonian framework it does, and Euclidean space is invariant on the translators and the rotation, that means you can rotate the laws of motion the way you want, and you get rotations for free, all right? And not only angular position, momentum is conserved, but also angular momentum will be conserved because there's an extra symmetry. So every symmetry gives you a conserved momentum quantity. Right? That's kind of the cool thing. Okay? So linear symmetry, so that means the homogeneity of space gives you a linear momentum. So a commodity theory gives you a price that is constant. Okay, the notion of a constant price, equilibrium price, comes from there. Okay. And we're going to construct spaces that are invariant on the rotations. This is this capital theory, and we'll get a price that is the analog of angular momentum, because that will be the conserved. For every symmetry, we can find a conserved quantity levels. This is a fun. So how many so there's another famous, as a fun little exercise. There's a famous conserved quantity called energy. Okay, so that would suggest there's a symmetry associated with energy. So every symmetry has a, you know what it is? Oh, that's hard, yeah? Oh, no, way too complicated. So if you can do an experiment and you can repeat it later, tomorrow, and you get the same results, you know, and if that when time is homogeneous like that, then you have the conserved quantity is energy. So it's kind of the momentum of time. Okay. You know, time is like this. That's why we have a law of conservation of energy. All right. that will be a consequence, but the energy is just the invariance, and you can think through that. You need to have that in order to make relativity work out, all right? But I wouldn't say that's why, all right? I would just say every symmetry has a conserved quantity, and the symmetry of the time, if you can shift all your thing forward in time and get the same results, that means there's a conserved quantity, and that happens to be called energy. This is much cleaner, You're looking too deep and far and philosophical, okay? Right? So for us, momentum is price. The price of what? It's the price of the goods, right? And what then is the surplus, which is the analog to energy? That must be the price of time, right? And that's correct, right? So the normal price is in currency per item, right? And the surplus is in what? The time, right? So you can think of the surplus as the price of time, or you can think of the energy as the momentum of time. There's the tendency for time to move forward. So if you have no energy, there's no time. All right? You have time, but it's just, you can't notice it moving. Right? It's still there. All right? That's interesting. All right? So angular momentum is then it's kind of the
It's funny, the
price of returns.
economic engineering in this case is easier to interpret than the mechanical case.
Yes.
Because the units just show.
Yeah, units are shown. Now, in your case, you already have the Lagrangian theory, so you know the change in the action. These are your costs that you make. All right, that's called the mechanical action. It's the price times how much you stocked up, right? Okay, that's the easy part, right? But also, while you were busy doing that, a moment of time elapsed in which you were not earning income or something like that. So you subtract this one, right? So this is then the price of time. It's a minus sign, it's not important. Okay, this is the way it was defined. It's called, as a famous equation, it's called the Poincaré-1 form or something. All right, in Hamilton-Jacobi theory. So this is just saying the marginal cost are the cost of the items you purchased and the cost of the time, right? So this is the price of time, this thing here. Or the negative of the income you received, the surplus you received, the profits you received while you have it. Okay. Actually, you can see it coming now. What angular momentum does is just a change in the returns, right? Times some other price, and that's the price we call angular momentum, right? Well, we'll get to this. No, but that's a good point. You see, in the economic engineering framework, it's kind of obvious when you write it down. In mechanics, this is extremely advanced way of looking stuff and Noether's theorem, and now that's just a weird thing. Now, I don't want to get into all this symmetry and Lie groups and geometric mechanics. It's very pretty, but what I do is I just talk normal, but nevertheless try to use the concepts from there because it's so enlightening, it makes everything so easy, So people, those students and even professors, it's hard to distinguish when do you use conservation of momentum, when do you use conservation of energy, what's the difference really? It's time, there is space, right? So if you have a spring, of course you're gonna, you can't have momentum conserved because the thing is pulling at your cube, right? But maybe it's also putting potential energy in there, so it's also, because it takes some time to do it, you also have some energy change, right? You also have to pay something. If you do it infinitely fast, you won't have that problem, but you'll find that that's not possible, right? The laws of nature don't allow that. Okay. Well, Newtonian mechanics would, you know. Yeah. In principle. Okay. So this is just commodities. So that's why we're interested in this as economic engineers. It's capital theory, because we're going to get new notions of price, you know, the price of land or the price of this and the price of that, you know, rather than just sticking to all these commodities. Now, the projects you have are just mostly commodity money, commodity this, but there's enough cases where you actually have capital and investment. So if you want to expand those models to have investments, you got to have some kind of rotations in there, some capital theory. All right. Okay. All right. Now, what I want to do is just get going with a simple example. All right, I'll work through it. Right? And the simplest example is actually not a rotation because there's like a lot of stuff going on. The simplest is a shear, you know. So you can think of a shear as a rotation of a really small angle, you know. So you know what happens when you have a really small angle, right? So you approximate the cosine by 1. And you approximate the sine by whatever the displacement, right? It's just linear, huh? Okay. Right? Now, if you kind of think that through, then what you really get is a sort of a shearing, right, of the plane, right? So the cosine always stays 1, and the sine just keeps growing. So you know, so here are these displacements you get, and it's a shear, all right? Sort of a limit rotation. You guys cool with that? So the idea, of course, of a shear is like, why do you need all these rotations? Because I just have this coordinate, I can do totally Cartesian and keep it constant, and then this one I vary. But you can still do this kind of rotational thing. So the problem you're going to have, the kind of leap of thinking you have to make is that because the cosine is always 1, this radius is always the same. So the radius of this arm is still 1, right? Huh? Okay. Now you look confused about that, right? Huh?
Yeah, but because you would think that it could like shear when the radius stays same.
No, but the radius is not the distance. You see, you're calculating the Euclidean distance, right? Don't do that.
Oh, yeah, of
You
course.
see, you just have. Think of this as if you totally contract it like this, right? So you make it very small. Then what happens to this distance? It stays the same, right? Huh? You see, because there's, of course, a very small little rotation, but you got to ignore that, right? Huh? Okay. Huh? So this, if the cosine is 1, then this must be, times the cosine must be, so you get this times cosine of that angle is equal to this, right? But if this is 1, you just get R is R, all right? Huh? Which is a little bit weird because I put it in, but then I have to say X at the end. Okay? Huh? So just keep that in mind. It looks confusing, but it really isn't. All right? Huh? Yes. No, look at this building. It's just shearing. Okay? I'm just saying you can think of it as a rotation. All right? No, you can shear like there's no tomorrow. Because you see, not every rotation is along a circle. You can have a rotation along an ellipse. It's just kind of a rotation, but it's a little different. You know, but it's basically the same thing because by a little rescaling, you turn it into a circle. Right? Understand? So just think of this as an ellipse, right? Yeah. You know, but this is like the minor axis, how they call this, and the other is the major axis. And you just put the major axis in infinity. There's no problem. So you see, it's sort of a limit. That's okay. That's okay. In fact, if they tell you in classes what angular momentum is in this, they'll use this, and they'll say angular momentum is conserved if you move along a line like that. Right? Why? Because you know the angular momentum is just twice times this velocity times. Here you'll see that this area here is the same as this area. Yeah? Kepler's laws are like that, right? So you got these rotations in ellipses, and you show that these equal areas, you know, the predicament in Dutch, huh? And here you see you have the same thing, all right? Huh? So it is like a rotation. But this angular momentum is going to be our price, and I want to just start off just looking at first the kinematics, right? Huh? First look at the kinematics, and then we'll put on the price. All right, but you see we're in good shape because angular momentum is a conserved quantity here, so we can use that as a price. All right, okay. So we're in good shape here. So, okay, so what we're going to do here is like the shear arm, you know, we'll just say it's equal to the absolute value of Q0. If you want, you can say this is equal to Q0 squared. The square root, right? Because then it looks more like a real, you know, it just means that you ignore the Q1 coordinates. Huh? All right? Okay? So that's just the formula for the shear arm. All right? And then the formula for the angular velocity, you just take last here, and there's some extension rate. So I forgot to talk about this a little bit, and I immediately went into that. So that's the shear arm. And then now go through these coordinates. So another thing that we do when we have rotation, we use this thing called polar coordinates. Okay, that's what instead of Cartesian coordinates. Now this thing looks like you might as well solve it with Cartesian coordinates. There's really no huge benefit, but you really won't, because you will just leave out this coordinate, and then you know, you will just use this one. But there's no problem dividing by it. Okay? And that's what they do. If you look at shears, they'll talk about the shear angle, you know. So they'll talk about the angle in which this building here is shearing, you know. They won't talk about displacement. It will be very inefficient because if you give a shear angle, you can tell me how much, then later on I can figure out where on the building I am and how much it's sheared, you know? So, okay. So, this is what we're going to call our capital. This thing doesn't change. Now, if you have something like land doesn't change. It doesn't get bad, it doesn't get any bigger, it doesn't come out of nowhere, right? So that's typically something that you would call that. It's called, we will think of this dimension here as a resource, and it's called an inelastic resource. Okay, so you can't really change it. They don't make any more of it, as Mark Twain said. All right? That's why some people thought that land is always a good investment. That's not true. And there are many reasons, and we'll find out what the value of land is to you, you know. But it's an inelastic resource. Okay, so land is a very good examples. You have also other examples. So if you have a bank account, like a checking account, they usually don't pay interest on it, right? So you just, you know, they do pay interest, but they don't compound the interest. Okay, so your money doesn't grow; you just get the interest. You know. A simple interest, it doesn't get compounded. All right, so they just keep paying the interest, and it shows up as interest. All right, but it doesn't get reinvested. That's called compound interest. So there's other examples, but land is a classic example. The classics only have three kinds of capital. They have, or they call it factors of production nowadays: land, labor, and machinery. Right, real capital. Okay. Later they added entrepreneurship. And that was supposed to take care of financial capital. We'll look at lots of capital. We don't care, all right? But land is the old capital, right? Okay. And then the other thing is the commodity that comes out of it. So this is land, it'll be some crop yield or something. All right. So basically, and I think I talked about this before, you see that there's something special going on here, that we're able to separate land out as something's different that can be owned by somebody, that you can have a stock of. All right. Now, that actually occurred in humanity at a certain moment in time. You know, I think it was in the Western world about 8,000 BC or something, when these hunter-gatherers settled down and did farming. You know, before that, land had no value. People would just walk around, and only the berries that were growing, that were the gatherers, or the animals that you could hunt had value. For the rest, the land was kind of there. That's how it was in North America too, and before the Europeans came. The local population didn't do much farming and didn't care, right? So in a hunter-gatherer society, the land is not worth anything, is not considered a commodity. It changes when you do farming. And then all of a sudden you realize you have two types of goods. You have this one good that you just have, you can expand, but it's a very different business. And the other, that is the crop you get, that's your operations, that's just flowing out of there, all right? So somehow you've got to get your whole piece of land, right? And then you start tilling this land. Now, of course, what happened was that other people who were still hunting and gathering, and this is all real history, they got a little bit, especially if there was not much, there was a famine or something, they got a little jealous of this individual, right? Who was having all this stuff. And he didn't really see why he shouldn't be able to show up and just take it, okay? Because the land was for everybody. So the person who's doing this, he's got a problem. He's got to defend that land and say, hey, this is mine. You can't just take it off. Now grab it and then grab the produce. Okay? So then since he's making so much food, that's called the surplus. All right? He had some extra food to give to a bunch of guys who were sitting there sharpening their swords and beating off anybody who would be so intrepid as to get this thing again, chopped up, and then we make an example of something. So you see, this kind of leads to everything. Now you have a separate class of people who are just in charge of this, this resource here. So all, and they become professional. They call themselves barons and kings, and they start wars in order to expand this, or they lose wars and then they do this. So they're in the business of getting this Q0, all right, the investment business, all right. And the farmer, he is in the business of getting the crops in the Q1 direction, right? I'm just putting that. And so you see these two different time scales start happening, and you see these professions coming in. All right. So in the hunter-gatherer society, there was just everybody was everybody, right? So sometimes they would have a scrimmage, and they would maybe beat each other up a bit, but those were the same people who were hunting, okay, or who were gathering, maybe, right? There was no distinction. There was no specialization. You get this kind of specialization when you turn into farming. And there's a lot of other specializations that come because now this can be taken to market. At the marketplace, you have to have this farming also at the market. You have other people making pots and pans, and then you go, okay. Okay. So this is an important step to make this distinction. And I would say this step is when economics is born. Because if you're just going around and getting some commodities, there's no price. You just want something, you grab it. Okay? And then you don't have to keep track of the price. Is the price high? Is the price low? It's only when you start doing this. And you need markets and stuff that you got to keep track of your prices. What do you want more? Is it more efficient to do better farming or more efficient to be expansionary? The Roman Empire was successful because it just kept expanding here. And then when it couldn't expand anymore, it kind of collapsed. It was built on expansion alone, right? We've been successful recently because we've been increasing this thing, right? This especially here in the Netherlands, we've just been very good at, taking a piece of land we have and putting out tomatoes and then this and that. So, in fact, until I would say 200 years ago, there were really only two professions. There was a warrior class, right, and then the rest were all farmers. Maybe there was a third profession, the priest class. There's the 3 estates, right? So that's me, right? That's the guys who are talking to get everybody to be on board, right? And somehow these guys that are working, they need to be told to keep working and relax about, not get too antsy, huh? So you need a priest class, so.
Those are fought wars, the priest.
What?
Also fought wars, the priest class.
Yeah, they would go along and motivate these. So that's how Christianity became big, because Constantine, he had a bunch of bishops, and these soldiers he was at the Battle of the Mill Hill Bridge, I believe, right? And he needed to motivate these guys and said, all right, if Mr. Bishop, if you do that, I'll make you Pope. You want to have power? Yeah, sure. Okay, well, if we win the battle, you get the job, right? That's right. So they're motivating people. And then afterwards, they had to, in the Middle Ages, the church really had to motivate. The peasants weren't very well off. They had a bad deal. But they had to get motivated to keep working. Nevertheless, all their happiness would be in the afterlife and something. That thing collapsed, I think, later. Yeah. So you see, society actually started, so you can, we're going to be able to calculate, what the incentives are to have an army, an efficient army, what the incentives are here for technological advancement. And we're right out of time, but I want to continue this now. Next week, we won't have, I'm going for next week, well, afterwards we'll go. This is really interesting, this stuff. It's really, I think, very, very interesting. There's so much what goes around you can understand, and you seem to be well on top of the historical.
And the hobby of mine.
Yeah, no, mine too, right? So it's interesting how you can trace the development of economics in this kind of way, right? Starting from the Sumerian and Roman Empire, and then additional forms of capital developing in the 19th century, right? So maybe a good project. Okay. We would love to go on, but we don't have time, so I'll stop here. Okay, and then we'll go on 2 weeks from now.